Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the blind Leetcode 75 problem list. Today I will be doing problem 128, which is called longest consecutive sequence. So let's get to read the problem statement. Given an unsorted array of integers nums, return the length of the longest consecutive elements sequence. You must write an algorithm that runs in big O of n time. So if we have this input right here, which is 100, 4, 200, 132, the output is 4 because we have 1, 2, 3, and 4 as the longest subsequence. Here we have 0, 1, 2, 3, 4, 5, 6, 7, 8. So 0 to 8, that's 9 numbers, so that's why the output is 9. All right, seems pretty straightforward. Okay, so if you want to stop the video right now to try this problem yourself, now would be the time to do it. All right, so the approach that I'm going to take to solve this problem will be a little bit different than the one that I usually do, and I'll be building a sort of a brute force solution, and then we'll just keep improving it with just one statement, and that'll make it'll make much more sense, right? So the algorithm, right, the problem statement is asking us to do it in big O of n time. So obviously, like probably the naive approach that you can take is simply just sort it, but that would be in n log n time. Just sort it and then just keep track of what the current longest subsequence is, and then just and you just return whatever the longest is. That's fine. But we want to do it in O of n time. So let's start thinking about how we could do that. So let's start with this right here, right? I guess the idea, right, whenever we try to find something that's like unsorted and we want to find like some consecutive elements, we always want to make use of some sort of clever way of using a data structure that allows us to fetch elements in big O of one time. So in this case, maybe a hash set or a hash map will be really helpful. And in fact, we'll be using a hash set. So first of all, let's think about what a sequence is, right? A consecutive sequence. So a consecutive sequence is just a bunch of numbers that follow this order, right? So if it starts at I, then the next element is I plus 1, I plus 2, I plus 3, I plus 4, and so on and so on. So what if we what if we start at 100, right? In order to know whether there's an element that goes after 100, we need to find whether 101 is here or not. We can do that normally with a list, but that'll take us big O of n time. So maybe it will be convenient if we just create a hash set that is just exactly this, that will allow us to find 101 in instant time. So let's just start with this as a hash set. All right. So we start with 100. And then if 101 is on our hash set, then we just keep going, but it's not. So the current sequence, like the length of our current sequence, will just be 1. So we'll have to create some sort of variable, right? That will represent what we want to return. And the idea is we're going to loop through every number in the set, and whenever we encounter, let's say we start at, suppose that it looks like this instead, because I'll show you like the little improvement after. So suppose we start at 2, right, in here. In 2, we have a 3 in the hash set, and we can look that up in O of one time. And we can keep just increasing the current number 4 until there is no number that goes after it, or 5. So then the length of this is 3. So then to return will be 3, and so on until we encounter the 1. So the idea here, right, is to store all the numbers in a hash set, loop through all the numbers in the hash set, and then we can call that the current number that we're at, we can call it like the current number, right? You can say that current number is equal to 2. And the idea is to run a loop So we can keep, and we also have to keep track of the length of the current sequence. So like the current sequence will be like 1 in this case, right? If we start in here, and 2. And the idea is, all right, so to return here is 1 because we've already processed 100. Assuming that it's in this order, of course. Usually when you hash things, the order gets, in memory gets messed up. I mean, there really is no order. But yeah. So the idea here is, okay, we have our current sequence with length 1, and in fact, I'm just going to write it down here. And the idea will be to do something like while current number plus 1 is in the hash set, right? We will keep increasing current num. So the idea is, okay, is 3 in the hash set? Yes, it is. So what are we going to do if it's in the hash set? Well, we're going to increase current number to 3. So we increase it by 1, right? And we increase the length of the current sequence by 1. And then in the next iteration, we check whether 4, so current number 3 plus 1, if it's in the hash set. If it is, we just keep doing that until, and we just keep increasing the current sequence until, in this case, 5 is not in the hash set. So we stop processing the sequence, and then we compare the current sequence with the largest one that we want to do. So let's get to code it. This will be almost a solution, but not quite. So I'm going to comment this out. And you'll see why I changed the order of this in a bit. But so first of all, right, we want to return a number. So to return is equal to 0. And then we have to create a set. That is the set of the numbers in here. And now we want to loop through it. So now, what are we going to do? Well, the current sequence, right, which is what we called there, is equal to 1 because we're starting at a certain number. And the current number is equal to 1. Not 1, sorry, num. Now, we're going to keep performing this operation where we increase this and then we increase the current sequence by 1. So while current num plus 1 in num set, we increase current num by 1 and then current sequence by 1. And this ensures, right, that we just keep increasing the sequence until there are no more numbers. So in this case, right, we start at 2, and then the length is 1. Then we go at 3, then the length of the sequence is 2. Then we go to a 4, length of the sequence is 3. And since there is no 5, then we get to a point where we don't need to, where we can't process anymore because 5 is not in the hash set. So after that, we have the length of the current sequence. And then if the current sequence is larger than this right here, then we have to set this equal to current sequence. So if current sequence is larger than to return, then to return will equal current sequence. And after that, we simply return to return. Now you'll see in a minute that this solution is not the most efficient, and in fact, you'll see why in a minute. I'm going to explain it, but let's just run it. It might even time out, but you see that it works with this code right here. But once it gets to really large code, it's really large inputs, it might not work. It might even time out. I haven't really tested this like in a little while, so let's see. Right, so it exceeds the time limit. And why is that? Okay, so let's go back to this example right here for a minute, right? What we're doing in the beginning is we're finding the sequence of 2, right? So suppose that we have a 2. We're finding the sequence of 2. And for 2, we go 3 and a 4. For 4, there are none. And then for 3, we go 3 and a 4. And then for 1, we do 1, 2, 3, and 4. As you can see, right, we're looping through the same sequence a lot of times. In fact, we're doing the same sequence once for everything, for every element in the sequence. I think with this, it might be easier to see. So let's start with 6, 5, 4, 3, 2, 1. This example will be pretty easy to see and understand. The main idea here, right, is that If this code right here will first loop through 6, right? Then it loops through a 5 and a 6, then a 4, 5, and 6, then a 3, 4, 5, and 6, 2, 3, 4, 5, and 6, because remember that we're just checking whether the next element is in the set, and we just keep increasing, and then 1, 2, 3, 4, 5, 6. So the runtime of this solution right here is big O of n squared, because in the worst case scenario, right, we're going to be performing, we're going to be doing the sequence over and over. So it'll be like n squared over 2 or something like that, the actual runtime, but it's big O of n squared. So how do we make this more efficient? Well, let's think about it for a second, right? If we're counting the sequence 3, 4, 5, 6, but this 3, 4, 5, 6 sequence is part of the longer sequence 1, 2, 3, 4, 5, 6, right? Why do we need to count this? And why do we need to count this? And why do we need to count this? Why don't we only count the longest one, the one that starts like this, right? And how do we know that the current one that we're on is the longest one? Well, let's think about it for a second, right? If we are in 3, right? 3, 4, 5, 6, how do I know that this is the longest one or that it's not? Well, all that I need to check is whether there exists a 2. Because if there exists a 2, that means that the sequence starting at 2 will be exactly one element longer than this one right here. So we will only perform this operation right here, like finding the length of the current sequence, if we can find an element. If we cannot find an element that is one number, like one number smaller than the current one that we're at. So for example, in 6 right here, if we're going to start a process, let's do the 4. If we're going to start a process to 4, right? If we want to do process 4, 5, 6, well, if there exists a 3 in the hash set, which it does, then it makes no sense to process the sequence 4, 5, 6. Because when we get to 3, we're going to process 3 and then 4, 5, and 6 again, right? So the idea is that whenever we're at the number, we have to check whether the current number minus 1 exists in the hash set. Because if it exists in the hash set, then there is, by definition, a longer sequence. It's the current sequence plus the number that's 1 smaller than it. So if we want to process 4, 5, 6, and 3 is in the hash set, then obviously the sequence 3, 4, 5, 6 is also going to exist. So there's no point in processing this sequence right here, right? So we will only perform this. So in this case, imagine that it looks like this. We will only perform this operation right here if the 3 is not in the hash set, because otherwise it doesn't make sense to do it. Similarly, if it looks like this, right? What this code will do is if we are at the 4, well, the 3 is in the hash set, so there's no point in processing. Well, when we get to process the 3, we're like, all right, is there a 2 in the hash set? And there is, right? Why would we process 3, 4, 5, 6 when we can process 2, 3, 4, 5, 6? So because there's a 2 in the hash set, we will not process this sequence. Similarly, when we get to the 2, we're like, okay, is there a 1 in the sequence, in the hash set? And if there is, then let's just process 1 in all of this. Like, why would we process this? It makes no sense, right? It's just extra work. So the main idea here is to simply wrap this in a statement that looks like this. So if num1, num minus 1 is not in num set, then we perform that. And this ensures that every time that there is a sequence, that sequence will only be processed once. So we're not going to be doing 6, 5, 6, 4, 5, 6, 3, 4, 5, 6, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 like we were doing before. Now all that we will do is 6, then 5, then 4, then 3, then 2, then 1, and then 1, 2, 3, 4, 5, 6. Which means that our runtime now is vastly reduced, and in fact, it's big O of n. And eventually, I tried with a couple inputs, but eventually this beats like 90% of solutions or like 80 something. But yeah, that's the main idea. The runtime of this, 85, there you go, good enough. But yeah, so that's the idea behind this algorithm, right? Like using the hash sets in a clever way, but make sure to not only look what's going ahead, but what could happen before you, like looking the number that's smaller than you. So yeah, the runtime now of this algorithm is big O of n, because for any sequence, right, we're only going to process it once. So that's pretty much it. And what is the space-time complexity of this algorithm? Well, the space-time complexity of this algorithm is big O of n, because we're creating an auxiliary set that helps us find the number of sets. And in the worst case scenario, every single number is different, so the set will contain n elements. And that's pretty much it. I hope you enjoyed the video. I hope that you found it helpful. Make sure to drop a like, which helps the channel a lot. And see you in the next one. Bye-bye.